Rocks of the Southern Alps of New Zealand. How the Southern Alps of New Zealand are built? Let's, an example of this mountain range, see how the mountains are building on our planet. In this video we'll talk about origin of the rocks, where they come from, and how they build the backbone mountain of the southern island of New Zealand. Southern Alps stretching for more than 500 kilometers, from Mount Asprey National Park in the south to the Nelson Lakes National Park in the north. Everybody who ever seen New Zealand on a map or visited it knows that the whole southern island consists of the backbone of Southern Alps, one of the most biggest and beautiful mountains in southern hemisphere. The Southern Alps characterized by different landscapes throughout, they're changing very fast. They say if you come to New Zealand, it takes you just hours or minutes to move from one type of landscape and geography to other. Icy peaks, forested flanks, deep beautiful gorges, amazing rainforest, tussock land and alpine environment, you can find it all just driving in one day throughout the Southern Alps. The main story behind it lies in the geology of that area, how it's been built, its composition, topography, and as a result, effect of the ocean and the climate on formation of beautiful landscape in Southern Alps of New Zealand. And that small role they play the earthquakes activity, volcanoes, and of course the glaciations. Maori were the first who found the passages throughout the Southern Alps from east to west, the main barrier on the southern island. Later the Europeans arriving there, following the footsteps, put the main highway crossing those passes. Today, if you follow the main pass, Arthur's Pass, you will travel through the history of geology, formation of the mountains, and also the change of the landscape. Let's have a look at that closer. If we start from the east and the gentle Canterbury Plains, what are the Canterbury Plains? Canterbury Plains are the material they've been brought by the glaciers and rivers from the mountains and nicely leveled was deposited towards the east. When you pass a lot of farms driving through the Canterbury Plains, you see the gradually ascending gentle slopes, and then highways start climb steeply into the tussock grassland. You will see the skyline of the mountain ranges at the background, and if you travel in winter seasons, they will be snow-capped. Much of the peaks of the Southern Alps are grey in color, and they're composed of predominant graveyaki, the main stone, the backbone of the Southern Alps. The formation of the Southern Alps started about 300 million years ago, and traveling westward, you will see the gradual change of geology, and as a result, we'll travel through the history. The majority of the Southern Alps are made of sedimentary rocks. In my previous video, we talked about Castle Hill and the basic geology of New Zealand, where I already touched about that. This sedimentary rock composed of layers of mudstone, alternated with layers of sandstone. In some places they have more creamier, brownish color, most of the time grey. This sediment was laid down on the ancient seafloor in horizontal layers, but the beds are now all deformed and nearly always inclined, folded, and often overturned, and they composed a little bit confusing masses, which represent the history of these mountains building. The name of this rock, graveyaki, comes from the German word. It means dirty grain sandstone that originally was found in Harz mountain of Germany. Mostly it's sand grains in the silt matrix, and they're all cemented into a hard grey mass. All this group of the rocks we called Turles supergroup, and it's named after the area of Turles Range in the inland Canterbury. That's where the name comes from. However, it's not just sandstone mudstones, but it's also some mixture of black mudstone, reddish volcanic mudstones, and in places limestone formations. Please see my Castle Hill Basin video about the limestone history. All these rocks were lying on the bottom of the ocean for over 200 million years. These Turles rocks was scraped and lifted over the big distance around New Zealand region, and we can find them from Otago to East Cape. and as far as beneath the sea in Catman Islands and Auckland Islands. However, not throughout this travel from Canterbury to the west coast, you can see same type of rocks. If you start looking closer, the more you move towards the Alpenfold, which is located towards the west part of the Southern Alps, the highest peak in the Southern Alps, you're noticing slight change in the rocks, and they become more modified the closer you move towards the west. These sedimentary original rocks being changed or metamorphosed. Thus, when two edges of the plate start meeting each other and sliding against each other, the rocks that be lying underneath start experience high temperature heat. As anything, if you wrap your palms together, there's some heat created. If you wrap it very fast, or even burn your palms. Similar happening with the rocks. The intensive movements, including very high pressure, which arising from not just the pressure of the two rocks crashing toward each other, two plates, you would think they're large, but also the hardness and the mass length of these rocks, they create enormous temperature and pressure. And therefore, the original rocks, sedimentary rocks, will reach some particular temperatures when they start a little bit melting, warming up, and they start modified and changing. For example, original sandy and silty material become a new type of rock. We call it schists. If you look on a schist, it's have a very platy orientation, and it shows you the direction perpendicular to this orientation where the pressure was applied, and sandy silty matrix start squashing, kind of stretching, and forming that type of rock. In New Zealand, Southern Alps, we call it Haast schist, after the geologist Haast. And you can find them across Otago, towards north, between Alpenfold and the main divide. To continue driving through the Arthurs Pass, you can actually observe the change when the rocks start changing from the normal grayish graviaki to the schist. We call it schistosity, when you have slightly modified and new minerals appearing in the rock, and you see this layering, metamorphic layering. For example, in beginning you see just a slight layering and just some pale green minerals, chloride there present, and the more west you're traveling, the more noticeably and pronounced schistosity become. You have formation already of shiny biotite, which you can observe through the rocks and give this nice shine on a sunny day. And towards the Alpenfold, we start finding a red garnet within the rocks. The minerals within the rocks under the temperature and heat, as I said, they are not just getting moved toward each other and squashed and stretched, but they also change the mineral composition, as any school's chemistry experiment will show you. Grains of sand and mud recrystallize, and new minerals grow perpendicular to the direction of pressure. Thus we form the slate and schist. And temperatures we're talking about maybe 300 degrees and the depths over 10 kilometers down from the surface. And the more you move deeper and the more you change the temperature and pressure, the different type of minerals will form, forming different type of metamorphic rock. Therefore, the deeper you're in towards the ground and the higher temperatures you see on this picture very nicely represented that the more modified rocks come out towards the surface. However, the moment you cross the Alpenfold on the west, the rock changed dramatically. Why? Because you're moving from Pacific to Australian plate. There's a very, very abrupt change, and the moment you cross the Alpenfold, you're on the land of ancient Gondwana geology rocks. And they'll be different. They won't be those squashed and metamorphosized Torlus group. They've been uplifted because two plates collide and start bringing material up. It will be the remnants of the Gondwana original bedrock, which been as well modified because of the collision and regional geology. This is the remnants of ancient Gondwana. Gondwana, the continent had been there more than 250 million years ago. Vast continent which occupied the southern hemisphere. The fragments of this ancient landmass are scattered around the globe right now. It's Australia, of course, Antarctica, India, Africa, and South America. In New Zealand, therefore, we can find only on this little west bit these remnants of this Gondwana land, and you can find it mostly in Fiordland, West Coast, and around the Nelson. These basement rocks are very ancient, they Precambrian time, and they're over 600 million years old. Therefore, in New Zealand, this is the oldest rock you can find, and in geology we call it Western Province. To the east, all the Southern Alps composed of newish Turlos group, which been modified, metamorphosized and uplifted, and this old province to the west. Therefore, in the blink of the eyes, you can cross the border of the Alpine Fold from 200 million years old rocks to the east, to the ancient rocks on which dinosaurs were walking on, which are about 600 million years old. In next video, we'll talk in detail how those rocks originally formed in the bottom of the ocean, Turles group, and Gondwana rocks. Therefore, I'll see you in the next videos about New Zealand geology. Stay with me and subscribe. Ancient sediments of the Southern Alps of New Zealand. In the previous video, we shortly discussed the formation of the Southern Alps of New Zealand, one of the biggest mountain ranges in the Southern Hemisphere. We talked about different types of the rocks you can meet there. However, we didn't discuss how they were formed originally, where they come from. Let's in this video talk a little bit in detail of two different types of rocks the Southern Alps composed of, and how they were formed originally to become a backbone of Southern Alps of New Zealand. All these rocks, which are mostly sedimentary, you can meet around the Southern Alps, started to build up on the sea floor back in the day when the Earth was different than now. We know that about 250 million years ago, the Southern Hemisphere looked differently from the space than it looks now. There was a one united single supercontinent known as Gondwana. Chain of volcanic islands stretched along the east coast of this Gondwana. Ash and sediment eroded from these volcanoes accumulated in the adjacent seas, and this sediment became the arc rock of New Zealand Eastern Province. Away from this part, another type of sediment was brought from Gondwana. It was slowly eroded on the land and brought by the rivers towards the ocean, and this sediment later became the Turles rocks. Different researchers suggested that those rocks mostly came from Antarctic area of Gondwana, and some now suggested that also from northeastern Australia. Surviving fragments of this ancient Gondwana are scattered now across our Earth, such as Australia, Antarctica, India, Africa and South America. In New Zealand, as we mentioned in previous video, Gondwana now form most of Fiordland, the West Coast and West Nelson, and it's the oldest rock you can find in New Zealand. Some of these rocks are date over 600 million years, Precambrian period. And in geology we call it Western Province, the oldest rocks of New Zealand crust. However, the most of the Southern Alps to the east from the main divide are formed from younger sediment of New Zealand crust, similar like a North Island. We call it East Province. These rocks go back about 200 million years ago of geological time, from the Carboniferous to the Cretaceous periods, and most of these rocks are sedimentary. Traditionally, geologists divided the Eastern Province into two groups, and we call them arc rocks, we talked about, and Turles rocks. Those volcanic ashes that settle down in the bottom of the ocean, and those material that have been brought from ancient Gondwana. All these rocks started in the bottom of the ocean around Gondwana. And geologists spent a lot of time to understand when and how exactly they were deposited and how they were brought together. East coastline of Gondwana, about 250 million years ago, contained a chain of volcanic islands, and they were spread for more than 1,000 kilometers, and it was talked a lot of ashes erupted and settled down on the bottom of the sea at that time. All these volcanic rocks were washed down and eroded into the sea. And its all processes were happening during 200 million years. And gradually all the sediment layers were building up on the ocean floor. We know these rocks in New Zealand in Southland, east of Nelson, and South Auckland. Near Lake Wakatipu, they form small part, and some of them were changed into schist. See my previous video about schist and metamorphism of the rocks around Southern Alps. Thus, different types of volcanic sediment will continue accumulated all around the island arc of the coast of Gondwana, while majority of the sediment you find right now around Southern Alps will form a little bit differently. Those materials, Torulous group, mainly light-colored minerals such as quartz and feldspar, must have been eroded from the land, consisted mainly of granite, this Gondwana land. And today we call those rocks Torulous rocks, and similar like are rocks that deposited for almost 200 million years, finishing in the early Cretaceous. However, the question where this Torulous material came from, very hard to pick. Material was broken off from the continent, Gondwana, moved by the rivers and then by the ocean, and then deposited on the bottom of the ocean. And then while it was uplifted up, it was modified. Therefore, geologists like a detective trying to figure out where in the past those rocks came from. We found that there's not so much volcanic material in those rocks, so they must come from the area far away from the volcanic arc. Scientists finding the granitic rocks of that type today in Mary Bird Land in Antarctica, and traditionally regarded this as a source of the Torulous rock. However, some modern studies of the minerals in Torulous have shown similarity with those in granite rocks of Queensland, Australia. And now, some geologists convinced that more probably Torulous group of the rocks coming from Queensland in Australia. And no matter where they were eroded from, of Gondwana land at time, today these rocks composed more than the half of New Zealand landmass. You can find those Torulous rock from south as far as Otago to the East Cape, and also in the ocean around the Catman Islands and Auckland Islands. Another puzzle about this Torulous group rock was struggling geologists how it was formed, laid down on the bottom of the sea. We see the very widely spread layers of grey sandstone and thin beds of sandstone alternating repeatedly with thin beds of mudstone. When you're in the field today, you can see those rocks very jigsaw puzzled and alternated. They experience so much uplifting movements and readjustments, squashing, that it's very hard to trace the one layer and the other. There's also not many fossils at all in those sediments, which complicated the job to reconstruct which layer is younger than which. That's why this is so hard to understand the original lay position of Torulous rocks and how they've been formed. Geologists struggling with this type of sediments around the world. And only recent advances in seafloor research, geology, give us some answers how the modern large fans under the ocean build up, formed from sandstones, mudstones, which scientists discover on the seafloor at the foot of the continental slopes, and from that we can reconstruct what might happen in the past. When you look on these beautiful fans under the ocean, you see the head of these fans, large valleys and steep side canyons, which cutting across the continental slope. We can see that layers of the sand running down through the submarine canyons into the muddy fan surface. We know that one of the largest in the world deep sea fan found in Indian Ocean, receiving the material brought by amazing river gang in Brahmaputra, and this went about 3,000 kilometers across. So scientists reconstruct how these fans are formed, and if you think about the ocean water, the muds build up very slowly with time from settled material in the water, which settle down at the base of the ocean. It's happening very slow, centimeters by centimeter. However, from time to time, big input of sand washed down by the rivers into those fens. Probably some kind of event, seasonal or strong storm monsoons or something like that, bringing a lot of material by the rivers, coarser material, and it's then flushed down into the canyons. Some of this material can cause even underwater landslides. It's speed up and mixed with seawater and form dense churning mass of sediment. It's moved down the slope in a great speed, disturbing the material from the bottom. And at the mouth of the canyon, this mass spreads across the surface, making the submarine fan. Eventually it's all settled down and blanket the muddy bottom with a layer of sand. And then the process repeats. You have another event when a lot of mud slowly accumulated on top of it like a layer, and then another event of a landsliding sandstone coming from the input from the river from the continent, bring a lot of material and a coarser material. Thus, observing this fence on the bottom of the ocean today, we can understand how it's happened in the past, and there's so many questions being answered to geologists who study the puzzle rocks of New Zealand we found on the surface today. For example, numerous conglomerates, the stones embedded in mud or sand, understood to be formed from the material that been disturbed within these submarine canyons or in channels of submarine fans. And we see the different types of deposition, alterating sandstone, mudstone deposited slowly in the quiet deep waters, and the sand deposited rapidly from the currents. However, we find some other types of rocks within this Torless group as well, and scientists suggested maybe not all of them were formed just specifically in the canyons. Some of those rocks were pre-existing rocks, and they were just covered by the sandstone and mudstones. Then the submarine fan spread onto them, burying the previously deposited volcanic rocks, seamouths, and calcareous deposits such as limestones under great thickness of sand and mud. And later it been become uplifted, mixed in, overturned, and exposed in New Zealand. Some of the Torless rocks suggested to be formed not under the water in the deep ocean, ancient ocean, but a little bit later accumulated in the river deltas of ancient Gondwana coastline during late Jurassic till middle Cretaceous times. There was similar formation of fans formed only on the land this time. Therefore, we can understand how this diverse Torless deposited group of rocks been formed all around New Zealand. However, we need to understand how it's been brought from the bottom of the ocean together with the arc rocks as well and formed into the mountains we observe today. To answer this question, look for my next video about Southern Alps of New Zealand, part 3, where we'll talk about the greatest forces of our Earth to move continents, demolish older continents and build new ones, known as the plate tectonics forces. Please subscribe on my channel so you will not miss new videos. How the mountains are built. The backbone of New Zealand, Southern Alps, were brought together piece by piece from the old continent of Gondwana and from the material in the bottom of the ocean. All these pieces being brought together by phenomena known as seafloor spreading, a process that constantly changing the face of our planet. Let's talk about how seafloor spreading shaped New Zealand over the last few 100 million years. First, we need to come back to the seafloor spreading concept. If we observe the world's ocean surface, we see the great system of mid-ocean ridges. This is the large crack through which magma, molten rock within the crust of the Earth, has risen from the Earth's interior and erupted to the sea floor. This magma that comes from within the bottom is caused by slow circulation within the mantle. Mantle, that's the upper part of Earth's semi-molten interior. So this flow of the mantle dragged the crust sideways away from the ridge. Piece by piece, with every eruption, this material solidified and added new basalt, a black volcanic rock, to the oceanic crust. And that's how oceanic crust characterized. We call it basalt, hard rock. At the same time, the forces are bringing this material away from the rift. Although it's moved only 10 centimeters a year, but over the long term, it can translate to enormous distances if you think in geological terms. For example, in just the time since the dinosaurs were on our planet till now, the seafloor can move the same distance as from New Zealand to Hawaii. You can imagine the effect of this spreading with time, which changing the face of our Earth. Although the main action happening within the oceanic crust, the molten lava coming up and move the plates, the real action happen where two sections of a crust are forced against each other. We can observe that the denser crust dive beneath the more buoyant crust and descend into the Earth's interior. We call it subduction, and the areas where it's happening we call subduction zones. You can see it nicely on the maps. In these places around the subduction, we find the deepest parts of the world's ocean. Watch my previous video about mid-oceanic ridges. With time, this material has been subducted under the plates, pulled downward by gravity, and helps drive the whole process of subduction and convection within the mantle. For all these remnants of sinking oceanic crust are assimilated back into the Earth's semi-molten interior hundreds of kilometers down. In the areas where these forces are occurring, we're not surprised to have intense earthquake activity. Geologists learned that by identifying the exact position and depths of each earthquake, we're able to build up a three-dimensional picture of subduction zones where it plunged into the Earth, like on this picture. As oceanic crust sinks down a subduction zone, heating may occur and cause parts of the rock to melt. Large bodies of the molten rock may then slowly rise up through the crust above. In these areas, the volcanic eruptions occurring, and we often meet the chain of volcanic islands or a line of inland volcanoes in that places. However, the most dramatic action occur when two plates of continental crust collide. The sediments that lie on the parts of the seafloor less dense than oceanic crust and do not pass easily down a subduction zone, so it doesn't get entrapped down under. Instead, they tend to be scraped off the underlying crust and squeeze into the collision zone. These rocks ramp onto each other and pushed above the sea and eventually form mountains. We know that the highest mountains on our planet, Himalayas, been formed exactly like that. Around the Earth, moving sections of the crust do not collide but simply slide past one each other along the large folds. We know them as transform folds. These folds lie within the oceanic crust, but some cut through continental areas such as St. Andreas Fault in America's west coast or New Zealand's famous Alpine Fault. Therefore, an hollow Earth divided into these plates, mosaic pieces, and boundaries between these plates are either spreading ridges or subduction zones. Or in some places we can indicate that it's transform faults, where plates slide past one another. We study that, and it's called plate tectonics, and I have numerous videos and conversations about plate tectonics. Geologists convinced that this effect was happening all the time on our planet throughout the whole history of our Earth. And we know, watch my other videos about the planets, that we find the same plate tectonics on other planets. those that are dormant, been in the past, or happening right now. Therefore, we can say that New Zealand been brought together by a seafloor spreading event. About 250 million years ago, plate tectonic played a major role in bringing various parts of New Zealand, which we observe now, together towards each other. At that time, subduction was occurring along the eastern margin of Gondwana. We know there was a chain of volcanoes. Island Vulcanus, which we talked about, resides not far from the continent. And we know that a lot of material was eroded away off from the Gondwana, called the Turlos material. See the part 2 of my videos about New Zealand mountains. And they built the largest submarine fans. As the sediment piled up, seafloor spreading slowly moved it towards the subduction zone when the arc sediments were accumulating. And like on a conveyor, this material was brought away. And around the times of Triassic period, the first of the sediment arrived at the subduction trench. And as we talked before, the heavy oceanic crust descended below the edge of the Gondwana, but this material, the sediment, was pushed towards it, and it was kind of beyond on top of it. It was scraped off the crust and squeezed against the sediment in the volcanic sea to the west. It's lasted about 50 million years, and this material was constantly brought towards each other. We don't have so much evidence because spreading ridges in the seafloor that carry this material no longer exist, so geologists have to reconstruct it by using the analogy. Calculations suggested that by the end of the Triassic, about 200 million years ago, this sediment has formed a crumpled mass tens of kilometers thick. And the more material arrived, there was a big pile of this material in the subduction. And eventually all this compressed material was pushed above the sea level, creating a new area of land east of Gondwana coastline. There was the first stage, which we called Rangitata Orogeny, named after the Rangitata River, where Turles rocks are well exposed these days. We can only imagine how huge those mountains were, and we do know there was a great thickening of the crust within the base of the sedimentary stack, pushing down into the top of the mantle. We know there was a high pressure in the temperatures because these rocks eventually metamorphosed into the Haast schist. Large areas of Otago formed from this rock, and all along the main divide. Today, geologists are able to date this schist rock. We use isotopic dating to measure the time when metamorphic minerals cooled during their formation. The Haast schist believed to be formed about 200 million to 160 million years ago, and we know it's time when the sea floor spreading and collision slowed down that moment, and the pulling up the material finished. However, what's happened straight after that, it's not very clear. There's not enough rocks on New Zealand to give us a clue, and we know that the sediment will simply never have moved into the region when the sea floor spreading stopped. From mid-Jurassic, we have again resume of this activity, and again more Turles sediment being brought to that area. And next 100 million years it was continue without stop. From mid-Jurassic to the mid-Cretaceous period, new fresh Graviaci sediment was continually scraped off the seafloor and bring towards the new land. And this material Turles group, which we found from North Canterbury to East Cape, it looks similar to the old Graviaci, submarine faint Graviaci material, however mineral composition slightly differ. And it suggests they were formed in the river deltas that were being carried away from different parts of Gondwana into the ocean. Today, geologists suggested that towards the first part of the Cretaceous, the collision was quite intense. And we differentiate two stages of Rangitata Orogeny. Second part of it started 100 million years ago, after the first phase of the collision and uplift created Haast schist. This schist was formed at the depths during Rangitata 1 and then pushed up by Rangitata 2, rising higher than the sea level within the crust in the south. And today we see this Haast schist all around Otago lying on the surface. This schist, which you observe along the Alpenfault is formed during later crustal movement. About 105 million years ago, this collision mountain building Rangitata Origine was over. The seafloor conveyor was switched off. How the seafloor conveyor was switched off, we don't know. But we know that by that time, New Zealand still wasn't as the one single continental body. It was somewhere at the age of the Gondwana, as combination of a Western Province rocks, turles, and arc rocks of the Eastern Province. And the new stage of evolution in New Zealand started, which we will talk in the next videos series about the New Zealand Formation. Please subscribe to my channel, post some comments, likes, and share this video on your social media so my videos could be promoted and I can continue doing my work. Thank you so much. The birth of Southern Alps of New Zealand. Last stage of New Zealand geological formation, how we know today. In the previous series of videos about geology of Southern Alps of South Island of New Zealand, we looked at how the New Zealand was built, from the material eroded away from Gondwana, brought to the ocean, built up from volcanic eruption, and then brought together to build the base of New Zealand. In this video, we'll look at the last stages of formation of Southern Alps of New Zealand till the present moment. During the first part of the Cretaceous, Rangitata uplift came to the end, and New Zealand region was mountainous and probably even higher than today. The mountains were made from the same turles rocks as today's Southern Alps, so the view was approximately similar like we've seen today in the South Island. Thus, at the end of Rangitata Origine 100 million years ago, New Zealand was a large area stretching several thousand kilometers along the eastern margin of Gondwana. Everything since we know as the late Cretaceous in Tertiary strata. However, most of these rocks were eroded. We can find isolated pockets of this material and reconstruct the story of formation of Southern Alps. In the early Cretaceous, there was not much material accumulated at that time. Most of the ancestral New Zealand was above the sea level and eroding away. This rock they deposited at that time could be found only around the east coast of New Zealand. The material had been accumulated during the dying phases of seafloor spreading. At that time, the erosion took over, and by the Middle Cretaceous, the mountains have been worn down to form extensive lowlands. There were numerous rivers flowing around the fertile plains, covering with vegetation. That's the time when the most of the coal will be formed and buried around Otago and Southland. Some of the remnants of vegetation found in that coal and between sandstone-mudstone sandwiches they preserved within show microscopic fossils and pollens, spores from plants that grew at the time in New Zealand. We know there was a lot of conifers, ferns and flowering plants, which were found across the whole earth at that time. The time still dominated dinosaurs, and the fossils were even found in New Zealand. We find some fragments of the bones. In particular, we know that pterosaurs, flying reptiles, were present in New Zealand, and the sea dinosaurs such as plesiosaur and mosasaur were present around New Zealand. Majority of that material that were removed from the continent were moved towards the ocean. And we find in the east side of the country some remnants of that material deposits. we can find some pockets of grey mudstones and sandstones very similar to the Torlos rocks. We can differentiate it with Rangitata deposits by presence of these fossils, and they tell us not just the age of the material, but also information about the sea life, who was living that time in the ocean. Numerous mollusks, fish, squid-like animals, and ammonites. There was also many marine reptiles, and we find the remnants of them in Eastern Otago, North Canterbury, Marlborough, and Hawke's Bay. At the time the erosion was reshaping the Rangitata landmass during the Cretaceous and make it flat. At that time, about 100 billion years ago, the whole region was starting to be pulled apart in the east-west direction. There was a big cracks developing in the crust, and a break-off happened. And the numerous eruptions of new volcanoes was indication of new breakup. We can find some remnants of it in Canterbury and Marlborough. The major split began, and the land started moving again. The ancient New Zealand began to separate slowly from Gondwana, while the magma welled up within the rift. At that time, the ocean flooded into the space opening between, and the Tasman Sea was born. We talk about this stage more in detail in the video on example of the Castle Hill rock basin. Watch my previous video about that. 85 million years ago, the sea floor spreading was fully on the way. New Zealand started moving towards the Pacific. By the time of 65 million years ago, the land had been largely reduced to low plains. In some parts, in central Otago and northwest Nelson, we could still see the surface of the old, flat Cretaceous landscape. Softer rocks were laid down on top during the Tertiary, but they were later stripped away to reveal the extensive flat area of hard basement rock. We call it Cretaceous peneplain. After New Zealand became independent from Gondwana, it's moved further and further from the subduction zone. As a result, the crust slowly began to cool and contract, become denser and sinking into the lithosphere. 30 million years ago, during the Tertiary period, the land started slowly sinking into the ocean. And by the middle of Tertiary, not that much of New Zealand left above the ocean. That time we know as the period of large accumulation of material all around New Zealand, not much of which actually preserved right now, only some pockets around the country. Watch my video about Castle Hill Basin. Most of this material you can find around the North Island and the pockets of preserved by the uplifting of the mountains in Southern Alps, where this tertiary sediment was kind of like a sandwich, protected from the erosion within the basins. Castle Hill, Arthur's Pass are the good examples of that. Studying these deposits, the scientists reconstruct the temperature and environment, life and vegetation at that time around New Zealand area. After this period, Oligocene, about 35 million years ago, this process all continues, and by the 35 million years ago, middle of Oligocene, New Zealand looked like just a chain of small islands. After that, the shoreline around New Zealand began to pull back from the land. New shore sediment became deposited further and further out as new land emerged. By the Pliocene, about 5 million years ago, large areas of land had risen from the sea. The big event with major proportions was beginning. This major event with a huge proportion started to affect New Zealand crust, and the new uplift has started. This last 5 millions, we have the new stage of mountain formation, which continues right now. We call it Kaikoura Orogeny, after the Kaikoura Range around the Southern Alps. And the main feature of this mountain building, it's the Alpine Fold, the feature that helps us to reconstruct, like jigsaw puzzle, the events, how material was shifted, where, which end up being in today's position. South Island been split in two by the Alpine Fold. You can see it very well on all satellite images, like very striking straight line. And this split start moving two parts relative to one another. If we shifted this two pieces of land back about 480 kilometers, we can match the pieces of the strata back together, and we see this offset happened during the last 25 million years. That's how much movement happened along the Alpine Fault. So how it's happening, how the material was moved along the fault, building mountains. To answer this question, let's look on the ocean floor. On the east of the New Zealand, there's a big mid-oceanic ridge that extends thousands of kilometers along the floor of the South Pacific Ocean. Constantly new crust, oceanic crust in this case, being constantly generated, and the ridges moving away on both sides. East of the ridge, the crust is traveling towards the coast of South America, and it's diving into the subduction zone, one of the biggest on our planet. On the other side, one piece of the Pacific plate is moving west towards the Australian plate. New Zealand located right in the zone where these two plates collide. If you're looking again on this bathymetry map of the ocean floor, you see the line along which collision is taking place north of New Zealand. We call that area Kermadec Trench. It's the place where oceanic crust of the Pacific plate is subducted beneath oceanic crust of the Australian plate. And there's also numerous volcanoes associated with that. Near East Cape, the Kermadec Trench merged into another subduction trench, the Hikurangi Throw, which ran east of the Hawke's Bay and Wairarapa. And that place, oceanic crust meets the continental crust, and it's subducted beneath the North Island. Thus, the North Island, numerous volcanoes been fed by the material which rising from the underneath in that area, and we know them like famous Tongariro, Ngauruhoe, Ruapehu, Rotorua, Tarawera, and White Islands in the Bay of Plenty, and also the Lake Taupo, part of the volcanic zone, and it represents huge, massive explosive volcano, one of the biggest in the history of humanity. From around area of Kaikoura South, the collision become more complicated, and both plates are made of continental crust. The continental crust not trying to slide one under another, and instead they just collide towards each other, and the Pacific plate suffer more and been squeezed more than Australian part, and it's scrambled and pushed up to build the mountains. The entire land composed of numerous cracks, we call them faults, and the largest one, of course, the Alpine Fault. This Alpine Fault directly divided Pacific and Australian plates. In the South Island, we find numerous fault systems because of that, which accommodate this pressure from the Alpine Fault. Even today, we keep discovering new faults all around. Pacific and Australian plates are sliding past one another, the crust on the west side moving north relative to the east side. The side wave movements is evident from the air, and if you match the rivers and some valleys, you can see exactly how it's moving recently. Alpine Fault exits the coast in Fiordland, and southwards from here movement between the plates is transferred back to the subduction zone. Here the subduction faces the opposite direction, with oceanic crust of the Australian plate descending beneath continental crust of the Pacific. That's in general the layout of the main faults and trenches around New Zealand, explaining where we can find which type of material and when the main movements are occurring. Let's then talk about what's happening since 25 million years ago this collision started. A lot of basalt has recorded the movement along these plates, and geologists can reconstruct it, the direction and timing of this sliding. If you look closely into a plate tectonics video, I talked about mid-oceanic ridges and how by studying the magnetism of the basalts we can time and reconstruct not just the direction but also the rates of the movement and building of the oceanic crust. Thus, let's have a look. 25 million years ago, Pacific plate began to collide with Australian plate, and subduction zone developed to the northeast of New Zealand. Continental crust prevented subduction zone to extend, and the crust began to compress and fracture, forming a major transfer fault, Alpine Fault. 10 million years ago, movement on the Alpine Fault was tearing the New Zealand crust apart. Rocks were displaced, Pacific Plate was advancing west, and all of the New Zealand region was being compressed. About 5 million years ago, New Zealand more or less started looking like today. Continental crust started narrowed in width and was crumbled up. Mountains were pushed up rapidly. East of the Alpine Fault, material started moving anti-clockwise and crashing into the Australian plate, pushing up the Southern Alps. At that time, we have those faults developing south of the Alpine Fault. Today, we see the subduction zone east of New Zealand now extended south almost as far as Kaikoura, the seafloor continuing to spread, and the crust under the very high compression. We experience this today by numerous earthquakes. Only in the history of New Zealand, only in the last 20 years, we have numerous large and significant earthquakes. The whole history of New Zealand followed by big activity, not just along the Alpine Fault, everywhere. Every day there's earthquakes erupting around New Zealand. We recorded these all earthquakes, even the ones which are barely could be felt by people with equipment, and we know that yearly we have about 14,000 of the quakes occurring around New Zealand. Thus the Kaikoura orogeny uplift of the Southern Alps started. We can tell that it started about 25 million years ago when this collision occurred. Plate changes from ocean floor subduction to continental collision. A piece of land being uplifted along the fault and the place around the Kaikoura. We have this representation of high land uplifted along the faults, and the close inshore seafloor dives to the depths of 1,000 meters. The place where we have a lot of upwelling, the current going around that area, bringing colder, richer waters from the depth of the ocean, and this attract a lot of fish, mammals, sea mammals, and in particular the whales. That's one of the world famous places to sight the whales. However, the greatest uplift happening around the Southern Alps, further down to the east and south. Scientists suggested, although it all started 25 million years ago, but only the last 5 million years, we have this accelerated rapid uplift, which continues today. You can see on this cross-section through Southern Island how the mountains being pushed up, how the Alpine Fault dips eastward at about 55 degrees, and the rocks at the west consist of granites and altered sedimentary rocks of Australian plate, while we see the schist to the east. And you can see the degree of schistosity throughout from the Alpine Fault eastwards. See the first video about Southern Alps when we talk about that. Scientists calculating the rates of seafloor spreading that the collision of the Pacific and Australian plates has compressed the New Zealand crust about 60 kilometers during the last 5 million years. Squeezing has gradually thickened the crust and pushed it up. Overall, the Southern Alps being uplifted more than 20,000 meters, about 20 kilometers. The material was constantly brought towards the Alpine Fault and uplifted, squeezed, pushed up. However, the erosion, such as water erosion, rivers, landslides, glacier activity, been removing that material and bringing back through the rivers towards the ocean. All this pressure is accumulated along this Alpine Fault and material around it during this long term, and as you understand, the properties of the rocks, they're very brittle. The property of the rocks, direction of the pressure and the movements of the plates, everything indicate of position of the faults, which we found today, and the Alpine Fault doesn't take all the pressure from collision of two plates, but it's also distributed into the adjacent faults that form all along, and especially towards the east. The Southern Alps, attributed to be one of the fastest growing mountains in the world, with a resulting uplift rate of 10-20 millimeters per year, which is mean that in a million years it will uplift about 10 kilometers. Geologists believe it has been accelerated only in more recent time, and then the bulk of the Southern Alps have been pushed up in the past few million years. Let's appreciate the erosion forces, which doesn't let the mountains be 20 kilometers high, but keep removing material constantly, piece by piece, rock by rock. In Southern Alps, eroded away as fast almost as they've been rising. If you've ever been around Southern Alps in heavy rainfall or high flooding seasons, you will appreciate how much material rivers carry. And that's happening gradually and intensively during the events like heavy rainfall all the time. And geomorphologists and sedimentologists take over from the structural geologist and explain the features we see right now around Southern Alps. And that's where the very tricky part comes in place to understand which material moved from where, how much per unit of time, and what does it mean for Southern Alps. We'll talk about some erosion forces around New Zealand, and especially Southern Alps because it's such a great example, one of the fastest growing mountains with enormous erosion. Stay with me, subscribe please, and comment on my video so more people could see this video and explore the wonders of our planet.